Explain generalized velocity and acceleration. Generalized velocity. Let a dynamic system consist of n particles of masses I varies from 1 to capital N, and at a time the system is specified by generalized coordinates qj is equal to 1 to n. Let Ri be the position vector of the mass Mi at a time t with that Ri is equal to q1, q2, qn, n comma t. Then Vi is equal to derivative of Ri with respect to t, which is equal to partial derivative of Ri with respect to q1, derivative of q1 with respect to t, plus so on, derivative of partial derivative of Ri with respect to qn, derivative of qn with respect to t, plus partial derivative of Ri with respect to t, which is equal to j varies from 1 to n, partial derivative of Ri with respect to qj dot plus partial derivative of Ri with respect to dt. The quantity n qj dot is called, which is equal to derivative of qj with respect to t, j varies from 1 to n, is called the generalized velocity of the system. Now, generalized acceleration. Since we know that generalized velocity is Ri, j varies from 1 to n, partial derivative of Ri with respect to qj dot plus partial derivative of Ri with respect to dt. This is equation 1. Now, differentiating equation 1 with respect to t, we get Ri double dot, which is double derivative of Ri, which is equal to d or dt sigma j varies from 1 to n, partial derivative of Ri with respect to qj dot plus partial derivative of Ri with respect to dt. Now, d/dt of first, taking d/dt of first one, j varies from 1 to n, d/dt bracket starts partial derivative of Ri or qj with respect to qj bracket close, qj dot plus j varies from 1 to n, partial derivative of Ri with respect to qj, this as it is, and now taking the derivative of qj, it is qj double dot with respect to t plus d/dt, then taking d/dt of Ri dt, partial derivative Ri over dt, which is equal to j varies from 1 to n, partial derivative of Ri dot with respect to qj dot plus j varies from 1 to n, Ri j qj double dot plus partial derivative of Ri dot dt. Now, putting the values of Ri dot from the equation 1 in equation 2, this is equation 2, and changing the inside form of j, we have Ri double dot in this equation, Ri double dot sigma j varies from 1 to n, partial derivative of qj bracket starts. Now, in place of Ri dot, we substitute the value of from this equation, and in place of j we place k. So k varies from 1 to n, Ri partial derivative of Ri with respect to qk qk dot plus partial derivative of ri with respect to t is into qj dot plus j varies from 1 to n partial derivative of ri with respect to qj double dot plus d over partial derivative of bracket starts k varies from 1 to n partial derivative ri q k with respect to qk dot plus partial derivative of ri with respect to dt. So in this equation, when we multiply with taking partial derivative with respect to qj, this will become j varies from 1 to n, k varies from 1 to n, partial derivative second del square partial derivative del square ri upon del qk dot plus j varies from 1 to n del square ri del qj del dt qj dot plus j varies from 1 to n partial derivative of ri with respect to qj double dot plus k varies from 1 to n del square ri del qk del dt qk dot plus del square ri del dt square. Now the Cartesian components of the acceleration are not linear, and the function of the components of generalized accelerations qj double dot alone, but it also depends upon the quadratically, the linearly, the generalized velocity components qj also. So that's in this way we can find the generalized acceleration and generalized velocity.